Morning. Oh, exciting. The excitement builds. Don't need to pay too much attention, but it's interesting stuff. Like synchronized swimming, I guess, right? Almost. Quite interesting. Somewhere off California. I guess one of these things did a trip from LA to Catalina Island, which I don't know, must be 20 miles. It's the island you see when you fly out of LAX. You go over it slightly into the Pacific Ocean, where Chinatown, the classic movie with Jack Nicholson, was filmed, about water rights in Southern California and how LA was built on some kind of mob water rights kind of thing. So today, I always think that pipe flow is kind of the most boring thing that we do because it's not kind of free form, it all fits into this recipe. Of course, that's good for being able to answer formulaic questions, but in some respects it's not so exciting, but I guess it's kind of bread and butter stuff. If you understand pipe flow stuff, we made the point yesterday of talking about similitude and how we have to have geometric similitude, kinematic similitude, Reynolds numbers are equivalent, and dynamic similitude, that the Euler numbers are the same. And we can, if we have that, we can use models of pipes, or we can use models of airplanes for external flows, or we can use models of ditches with flow in them for free surface flows. And we don't have to know anything about the governing equations, but we can just do experiments and calibrate those experiments, which is how we get the Moody charts, as we explained last time. So this is kind of, I think, is maybe an interesting way to look at pipe flow, because obviously this is pipe flow. You have looks like a jet ski in the bottom, which is a pump supplying pressure to water that it takes from underneath it, and it goes along a pipe and it squirts out of a pipe, and it's able to do these things. And so one thing you might want to do, and it wasn't Thirsty Thursday for me last night either, is to be able to size the pump that you'd need to be able to make this work. We could guess all of the components of it. And so I'm not sure we'll come back to that movie, but this movie, but I'm guessing that if you combine the two jets of water, it'd be something like a 4-inch diameter jet or something, or 4-inch by 4-inch jet. It's so much easier to calculate areas on square things. And so we'll come back to doing that as part of the class, right? So that's what we'll do today. So, of course, we'll start off with something more mundane than that, just to recap where we've come from. We finished off with the Moody charts yesterday. So we're starting to pull things together. Hurricane Marcella? It's Marissa, I guess. Is it Marissa? Melissa has done a thing with wreaked havoc across Jamaica and Cuba. We talked about the energy equation, which is week 8, which is just the Bernoulli equation with head loss terms. So we've kind of talked about one of these head loss terms, the so-called major head losses in pipes, and we'll talk about minor losses. We made the case that we can get the equations for pipe flow by satisfying dimensionless analysis, that it should be model pipes that are exactly the same. So the characteristic dimensions we have to honor are length to diameter ratios and the roughness to diameter as some measure of what's going on. Kinematics would be that the Reynolds numbers between model. So the model, if you had a pipe this size and you want to have a pipe this size and you can't get in the lab, then you'd want to have the Reynolds numbers matching, which means the flow regimes are matching between model and prototype. And if that's the case, then we would calculate the pressure drops in each of the model, measure it in the model, and apply it to the other system. We made the case why we should have Euler numbers and Reynolds numbers just by a simple example, plot in some way, and they turn up in this so-called Moody chart. So that's what we'll maybe work from today. So let's start off with just recapping that. So we'll talk about major losses, I guess. So we go. And so actually, why don't I write out the equation? So we know, just, you know it, but let's have it down there. We have to write it from upstream to downstream, as we talked about yesterday. Not yesterday, 2 days ago. And so 2 is downstream. You know, hopefully, that the difference between my p's and my rho's, not very much. 2g plus sum of the major losses and the sum of the minor losses. We know that, I don't mean to just repeat this unabashedly. Am I doing something wrong? Pump losses, positive pump, negative turbine. And this is uppercase W. This is power. Sometimes we've called it uppercase P. And these two components. This is what we spent our time on last time, that the major losses are for pipes, and it's equal to a friction factor multiplied by length of the pipe to diameter and V squared over 2G. Importantly, this is velocity at point 1, which may or may not be the velocity in the pipe, depending on where we take it. Right? We did this two-tub thing. The velocities, if we did it on the surface of the flow from left to right, was 0, and so that's what this would be. If it was done at the beginning of the pipe and the end of the pipe, it might not be 0, but if the pipe doesn't change diameter, they would at least be equivalent to each other, so they would cancel out on either side. So that's what this would be. And so, we didn't make the point here, but we said that head losses for fittings, going around bends and going through faucets, for instance, would be, we've done it in one of our examples, a loss coefficient, V squared over 2G. So very specifically, this is V bar. This is the average velocity within the pipe or the fitting that goes on these. And so we have to at least be aware of that. From this, we develop Moody charts. I will do one thing. You remember, perhaps you won't remember. It's not so memorable. But we definitely looked at, when we talked about the energy equation, we talked about differential forms of the energy equation. This is epsilon, and that's just the peak to trough, peak to valley distance on the roughness. We have an average velocity coming through the pipe, just means it's uniform across the section. What else do we have? We have density and viscosity of the fluid that's flowing, and I guess we have delta P, this driving flow, and length. So that's our standard form. That's L. And so you might remember that if you solve the Navier-Stokes equations for this, which came from the momentum equation, with viscosity added for losses, which we didn't dwell on too much, we ended up with a solution which was the average velocity across the pipe is equal to the pipe diameter squared over 32 times the viscosity, and the pressure drop over dp, delta p, over the length. And in this, delta p over gamma w would be equal to the head loss. And if we wanted to, we could manipulate that. I won't do it. I'll just do the result. So you can take this, you can substitute delta p being equal to, he says he doesn't want to do it, but then he does it, head loss times unit weight. So if you substitute this into here and manipulate it to get it in terms of HL, once you've got it, it ends up being that HL is equal to 64 over Reynolds number. And you'll see the reason for doing that in a minute. L over D and V squared over 2G. V bar squared. And so we've seen this before. So this term here is actually our friction factor for laminar flow. So this is F L over D V squared over 2G. And so I'll come back down here in a second. This is exactly what we would get if we plotted Euler number versus Reynolds number for doing the experiments in a pipe by just jacking up the pressure in a single pipe and measuring the change in flow rates out of the system. We kind of did it last time. And so this is true for laminar flow only. And that would make our, what do I want to draw? I'm going to draw the Moody chart just by hand, just because I can introduce the most important features. So it's a log-log scale. It's a Reynolds number, which is equal to the average velocity, the density of the fluid, and a characteristic dimension. The most logical, you could use length as a characteristic dimension or the roughness, but it's most logically the diameter. And instead, I guess it's yeah, I'm sure. I just drew this as friction factor, not to confuse things. It's a surrogate Euler number. It's kind of friction factor. And so the only things we're interested in are we have an ordinate on here which is about 2,000, 2 times 10 to the 3. On one side of this, I haven't looked to see what it's doing. On one side of this, it's turbulent. The other side, it's laminar. Of course, laminar means that if you look within the pipe, it's this parabolic distribution, which would come out of this. This solution is for parabolic distribution, which we change to convert to an average volumetric flow rate and assume it's uniform across the pipe. And in turbulent flow, it would be, what happens is that you get this uniform distribution. So what is happening is that you get along the boundary of the pipe, you get a boundary layer flow. And so all the shear, this behavior here is because we satisfy, I'm going to go off into a side tangent I get. We satisfy Newton's law of viscosity. This would be y, the radius would be y. So the velocity in the x direction, this is the x direction relative, the change in velocity in the x direction relative to y. So it's kind of it's this slope as it changes around. And so this slope means that there's some resistance to shear stress, and this is the frictional loss that goes in this head loss. If you have a turbulent flow, then it's easier to think about it, I think, in terms of, say, flow past. It could be a golf ball. And we know that if you have creeping flow, where all the losses in the system are due to viscosity. It's this, it kind of hugs itself, and all the streamlines would be adjacent. We'll talk about this in terms of external flows. This one is the opposite, is different in that this is, for want of a better drawing, these eddies that go behind it. And so I say this could be a golf ball because golf balls are specifically pitted. They have dimples on them because it makes the flow turbulent earlier for a lower Reynolds number than it would do otherwise. And it turns out that this is a more efficient way to be able to push the golf ball through the air. You wouldn't think so. And it's because a boundary layer forms right at the edge of the boundary between the static surface and the moving water. Very high gradients of velocity from 0 to average velocity over a very small distance, and that's a much more efficient way to have it flow. So this Moody chart is that this is in the turbulent regime. This is friction factor is equal to C over RE. And for a circular pipe, it turns out that C is equal to 64. This term here. So as you look at this, this is this exactly. And you have these two regions, laminar flow, transitional flow, and turbulent flow. And so I'll draw that on this diagram. So there's a transition in here, and then if I draw it in its most simple form, then I would draw this. Perhaps I'll draw it in red since the other stuff. No, let me draw it in green. Not that color matters. And so you end up with this. So the bounding values are that this, if I can draw this, I'll just draw it a straight line. So if you look here, the label on this is for smooth flow. And so these represent different magnitudes of roughness. So this is a big roughness. This is a small roughness. This is for smooth flow. So I guess epsilon over d equals 0. A glass pipe, if you like, glass tube. And so this isn't quite the deal. This is a region of sometimes called a transitional region between truly laminar flow. I guess the word laminar flow is because you can think of this as a deck of cards. They're all laminae just shifting over each other as it flows downstream. If you looked at the flow patterns in here, you'd find that they're doing this, lots of little vortices. In fact, I think, all right, if I do this and do this, you'll see exactly what that is. I don't think I looked at it. I think it was 10-1. Come on. Yeah. So this is a tube with a dye tracer in it. And so this is traversing exactly downstream. It's going, you could imagine it's a deck of cards across the height of the pipe, and each one is just translating over itself. The ones on the pipe edge are locked, and the ones in the middle are going the fastest. This is obviously the Reynolds number all the way along this pipe has to be the same. So this is just an effect of being further away from the inlet. But it is showing what this would be turbulent flow. So this is little vortices you can imagine going down the center. If you went otherwise across the section, you'd also see these vortices. And if you took the average of these vortices across the width of it, you'd see it, in average, it would be a block moving at kind of constant velocity all the way across the height of this pipe. Whoops. And so that's what we mean by this. So I'll make sure I turn that off so it doesn't compete with me for bandwidth on the voice. And so this would be exactly that. If you look down this tube, you'd see vortices. So that, but on average, this would be a straight line across here, right? If you went across here, the instantaneous velocity might be a lot in one direction or the other, but the average would be some magnitude, which is given by V bar. So we can use this chart. We can get this chart without any differential equations just by using dimensional analysis. And that's how it was derived in the first place. And what else do I need to say about that? I don't think I need to say anything about that. I guess the other one thing that I should say, and we said last time, is that the characteristics of this are that in the turbulent regime, then the friction factor is a function of roughness, but not Reynolds number, right? These are horizontal, so it's a constant value of friction factor in here. And in the laminar regime, the friction factor is a function of Reynolds number. Because, obviously, it's a function of Reynolds number. And it changes as a function of the Reynolds number. And so that is interesting. It means that this characteristic flow between laminar and turbulent exists for external flows. If you're flowing around a plane, it also exists essentially the same chart for open channel flows, flowing in a river or in a ditch, that you gravitate from laminar flow to turbulent flow. It's indexed by Reynolds number, always. And the fact that it's a function of Reynolds number makes some problems to solve more straightforward than others. So you have to realize that in the turbulent regime, it's a function only of roughness, which is useful because then we don't have to know what Reynolds number is. It's independent of that, other than that we're above the lower threshold of it. But if we do it within the laminar regime, we have to deal with things in slightly different ways. Okay? So that's pretty much all we need to know about this. The other item that we talked about here, which we should deal with, I'll deal with quickly, is that there are also minor losses. So these are called minor losses because individually they're quite small, and they only occur at bends in flow, for instance. So these are for flow around a bend. This is for flow in a pipe. I drew these little pictures before. So these are minor, but over a pipeline that goes from Louisiana to New York, the long distance makes it a major loss. So that's the reason for the terminology. So we'll come back and we'll do a jet lev soon, but let's just zoom through this. So this is the idea, that when you have fluids going from zero velocity here to accelerating to some other velocity here, then there may be a loss by the geometry that you have. We can calculate that head loss as being equal to a loss coefficient multiplied by the average velocity in the pipe squared, or the velocity head, I guess it is, right? This is the average velocity in the pipe. So it'd be the velocity here, not the velocity before it goes in, because this might be zero, right, along a streamline. And the fact that we will see that they can usually be denoted by a single magnitude for this, independent of Reynolds number, means that for pipe losses, we're probably in this regime here. We're always treating them as turbulent because they're flowing through a constricted space, and the behavior is not laminar like a deck of cards, but turbulent. And it would, if you have the velocity going from location 1 to location 2, and you imagine somehow, just like the truck on the apron at San Francisco Airport, that the velocity where it stagnates against this is going to 0, I think the maximum magnitude of this loss would be equal to 1. It's going from some big velocity here, v squared, stopping at a wall, and the magnitude equivalent loss coefficient would be a 1. And so where it's a nice gentle acceleration into this pipe, it's not a very big number. Where it's a really dramatic acceleration into the pipe by a nasty geometry, it's a relatively large number. You see all these numbers are bounded by 0 and 1, kind of fitting with this idea. And so you get losses if you're going into a pipe. You get so-called vena contracta effects, which you get separation from a flow with a little piece of dead zone, no flow in this, just stagnant material. and you can calculate what those are. I don't really want to spend much time over it. You could imagine that as the radius of curvature of this gets larger and larger, that the loss coefficient would get smaller and smaller. So as you get a very gentle entry into the pipe, the loss coefficient, K sub L, you expect to get smaller. And we also get exit losses. So in other words, where you're going from V1 here at the average velocity to 0, then you get, just as I said, a loss coefficient of 1. You're going from some velocity, you're going into a stagnant tank, and so the velocity downstream at 2 may be equal to 0, and therefore you'd expect to realize the maximum loss. And so you can't necessarily get rid of it even by having a more gentle entry into the system. So all we need to know is that they exist and that we can calculate them somehow. So I'm not going to debate on that. You can imagine that you could define it in terms of the relative areas. Here, if area 1 or area 2 is equal to area 1, then this ratio of areas would equal 1, and the loss coefficient would be 0. Because you're going from velocity upstream to velocity downstream. I guess you could argue that over this length, there should be some friction factor applied, but it's such a short length that you don't care about it, I guess is the case in this point. And blah-de-blah for all these different things. You get it when you flow around bends. You could make it less by having guide fins within the bend to make the transition more gentle so that you don't get this vena contracta effect with separated flow that's stagnant here, static water here with water rushing around it, and the flow therefore restricted to only part of the cross-section. And of course, if it's only restricted to part of the cross-section, it has to accelerate from a velocity here to a larger average velocity here. And so that's the reason why it might work. When you go around bends, if you go around a horizontal bend, you can imagine a separation in the middle of that bend where you get circulation on either side of that mid-side line, which is really what's being shown here, as a secondary flow, and you could work that out. And this is perhaps the only thing that we'll need to really understand here. And that is, one, that you can calculate what this loss coefficient is. So we'd like to calculate it as the sum of the loss coefficients times average velocity. And it should be the average velocity in the pipe that precedes it or goes after it, follows it. So this would be the velocity in the pipe going into it. And it matters that the number is bigger depending on the characteristics of the pipe. So flanged means that you have a smooth transition between a pipe being joined to another pipe by a bend, right? Like a copper pipe. You solder them together. And a threaded transition would actually have some of the threads present within the pipe flow region, right? You could imagine this. So more resistance here. So the resistance for the threaded pipe being larger than for a flanged pipe. If it's a long radius, so it's more gentle, larger radius of curvature, then it would be lower. If it's threaded, it's higher than being flanged. If it's a long radius, in either case, it would be lower. And if it's only 45 degrees instead of 90 degrees, also you'd expect it to be less as well. If you have a 180 degree bend, again, flanged versus threaded, not quite conforming completely to what I said about 0 to 1, but kind of, you get the picture. T's, of course, some T's could be open. If flow could occur within this, but because you had a valve on here that was stopping flow, then the flow down here would recognize it's a kind of uneven portion of the pipe, and you'd get some resistance due to that if it was only flowing. If this was open and it was able to flow up into this pipe at some velocity, then most of the flow goes down, or perhaps all of the flow goes down, and you have the downstream portion blocked. Whoops. Then you'd get a larger magnitude of KL because it's going around a bend. It's essentially doing this in a different geometry, right? And if you have two pipes together, and if it's threaded, so in other words, you'd see threads here, then you get some instantaneous reduction in addition to the friction factors that you'd see on either side, right? which we'd have to accommodate for. And the big ones, of course, is if you flow through a valve. And so the idea is that if you have a valve, I guess in this case you'd be flowing into this chamber here. It's almost like a heart. You unscrew it, so you lift this platen or this stamp, what would you call it, so that the flow, once it was lifted, it would go through this and outside the other place. Then because it goes around a bend, as you lift this up, then this has some resistance to it, and you get a loss coefficient for this. Likewise, this would just be a straight flow through the system. It's closed off by having an anvil, I guess was the word I was looking for. You close it by pushing the anvil across this, so there's no pathway across this where it's closed. But at least as it goes across here, it's going in a straight line. This has to deke around to do this. And you could imagine that you'd have different values depending on the severity of the rerouted flow across the system. So that's all we need to know about these. So let's go back to our JetLev and do an example, just because we can. So got it written down here, so let's see if I can get this right. So what do we have? Yeah, I don't know why I did this. So here you go, just I can get artistic. Oh, not yet. Recognize it yet? Okay, let's do this. I won't obscure all that I've done now by doing this, but let me do that. So this is our system. And so we're going to go from upstream to downstream. So let's this be our point number 1. Let's this be our point number 2. This is our pipe. Let's put some parameters on here. What do we think? How heavy is a person? Good enough. I guess he's got some hardware on the back as well, right? What are we going to solve? Well, here's the calculation sequence. We want to use the mass of the person to calculate what I'll call W2, the velocity of the jet. So we'll be able to calculate that from the energy equation, conservation of momentum rather. If we have W2, we can calculate the Reynolds number. If we know the Reynolds number, we can calculate the friction factor. And if we can calculate the friction factor, we can calculate HP. And if we calculate HP, we can calculate the power in this pump. That's it. And so we need to be able to define some things. So I'm going to put some easy numbers here. The area of flow, I'm going to have, I said 4 inches by 4 inches. So that'd be 10 centimeters, which is 0.1 of a meter, times 0.1 of a meter. So this is going to be 4 inches by 4 inches if you want it, but we can write it as 10 to the minus 2 meters squared. We're going to have a square pipe. So this is A, and this is diameter, just because it's easy. So A is equal to pi d squared upon 4. This in my simple mind is equal to 1. It's gone off the screen. I don't know why it does that. But it hasn't come back. Oh, yes, it has come back. And so to my simple mind, this is 1. 3.14 over 4. So d is equal to 10 to the minus 1. And let's put some other components on here. So what did I put down to make it easy? Yeah, it doesn't quite work out this way. So this is 6 meters, 1 meter, 1 meter, 1 meter, 1 meter. So 6, 7, 8, 9, 10, making life easy. And I guess the valves and the exits and entries would be 1, 2, 3, 4. I had an exit here. I guess you could imagine that one could be here as well. So I won't number them, but this is 1, 2, 3, 4, 5, conveniently. And so we need to use our energy equation, which will be, if I take this and just write it conveniently out slightly differently. So let's write this out on one side. How are we going to do it? We're going to want to be able to define things in terms of this. So let's move everything off to the right-hand side that isn't this. So if you write the equation for this, it will be HP is equal to Z2. Z1 has come from the other side, plus P over P1 minus P2 all over unit weight, plus V1 squared sorry, this is wrong, right? Already wrong. These are 1s. This is 2, and this is 1. And this would be sum of the major losses and sum of the minor losses. And we need to define exactly what our components are, right? So what are they? Well, Z2 is equal to plus 1. If we take our datum as there, right? Actually, and pressure comes in, atmospheric pressure here, goes out, atmospheric pressure here. So these are both 0. Not that they cancel, but they're 0, and they do cancel. And here, I guess, we could imagine that this is a big tank assumption. So V1 might be 0. If you take it, for instance, here, bless you, along a streamline. But V2 certainly isn't that. So this is what I'm going to call it W2. And then we have to figure out what these things are as well. Okay. So I missed out the first part. So this is the momentum equation. And so you'll remember the momentum equation is that the sum of forces is equal to the sum of velocities times mass flow rate. With dimensions attached to it. So this is going to be, so in this equation, the only components we'll have would be the force, which is drawn on here, would be minus F, because it's pointing downwards, just as I've drawn it. This, for the energy equation, would be This is mass flow rate. It's out of the system, so this would be positive, if you can see that. And the Cartesian direction for this would be in the negative z direction, so this would be negative. So this would be minus F is equal to minus W2 squared times rho A2. And this would be equal to mass times gravity. This is 100 kilograms. Used to weigh myself when I came home on the train from the pub. Used to be 62.5 kilograms at one stage on the train station. And this is 10 meters per second squared. And so we can solve that in terms of, we want to solve for W2. So W2 squared is equal to mg over rho A, which is equal to 100 kilograms times 10 divided by density, kg per meter cubed, and area is 10 to the minus 2 meters squared. Getting a bit crowded. So this would be 10 to the 2 times 10 to the 1. So I guess that would be 10 to the 3 over 10 to the 1 minus 1, 10 to the 1, which would be equal to 10 squared. I won't do the unit conversions, but if we've done everything right in kilograms, meters, and seconds, then we should be getting things in newtons, etc. And so this is W squared. So W equals W2 squared square root, obviously, equals, conveniently, 10 meters a second. Not an unreasonable number. So at least we've got that. So we're at this point here. So we have this. So now if we want to solve the chain for the pump, which we'd like to work through, we need to know the Reynolds number, because that will give us the friction factor. If we have the friction factor, we can calculate the major losses and the minor losses. We don't need the Reynolds number for that, and we can calculate that. So I guess we need to know, also we need to know HL minor. So this gives us HL major, this gives us HL minor. Okay. So next stage. Reynolds number is equal to velocity, density, characteristic dimension, and viscosity. The numbers for these are 10 meters per second. Density is 10 to the 3 kilograms per meters cubed times 10 to the minus 1 meters, right? 10 centimeters was our diameter. It was just the square root of our area, because we're assuming a square cross-section pipe, just to make life easy. And viscosity for water is 10 to the minus 1, 10 to the minus 3, sorry, Pascal seconds, which is newtons per meter squared per second. And if we work those out, this is 10 to the 1, 10 to the minus 1 cancel out. So this is 10 to the 3 over 10 to the minus 3. Should be dimensionless. Pascals will be newtons per meter squared. Kilograms, meters per second squared is a newton by definition, right? A newton is 1 kilogram per meter, or 1 meter per second squared. And so this is equal to 10 to the 6 Reynolds number. It's by definition non-dimensional. If we go back to our Moody chart, we go to 10 to the 6. Let's assume we have a nice smooth pipe. And this is, I misread it, I read this as being 0.02, but of course it's not. It's 0.011, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, etc. So this is our friction factor for the pipe. Let's assume all the pipes are the same friction factor, because they have if they're all the same diameter, they'd have the same flow rates through them. And so we can calculate from that our other magnitudes. So the head loss major is equal to friction factor length over diameter v squared over 2g, which would be equal to 0.01. I won't use the other one. Length, conveniently, is 6, 7, 8, 9, 10 meters over, our diameter was 10 to the minus 1 meters, multiplied by v squared, well, I'll just write it out. What was our velocity? 10 meters squared in meters squared per second squared, divided by 2 times 10 meters per second squared. Let's see how good my math is. So this is 10 to the minus 2, 10 to the 2, so those cancel out. So this is 10 divided by 10 to the minus 1 times 10 is 1, I guess, divided by 2, which is equal to 5. Is that right? Ten to the minus 2. Yeah, fine, let's go with it. So that wasn't what I got before. So the minor losses are going to be HL equals sum of KL times V squared over 2G. Yeah, I know what I did differently, which is equal to 0.2. Well, let's do it. We haven't said what those would be. So this is an entry or exit loss. This is a bend. This is a bend. This is a bend. This is a bend. And so let's just use K sub L equals 0.2. That was a commonly occurring number we had before. And conveniently, this would be 5 of those. Sorry to be so pedantic, times V squared over 2G. This is the velocity in the pipe. And I guess what I want to do with this is I'd like to write it out as a friction factor times length over d times v squared over 2g, but keep this equation out. So let me rewrite the energy equation. So the energy equation that we had will be this. So this is what we want. So the main components of this is you have a head, which is just how high we are at the outlet versus the bottom surface. We have these terms here. We have v squared over 2g, and each of these terms will also be a function of v squared over 2g as well, right? Because they are this. So if I write that out, I would get this. HP is equal to 1 meter plus v squared over 2g plus friction factor, length over diameter, sum v squared over 2g plus the sum of the head losses times v squared over 2g. So I do that because each of these terms here turn up. This is this. This is this. And this is this. So we can get the pump head to be equal to 1 plus 1, that's right now, v squared over 2g times 1 for this term, plus friction factor length over diameter plus sum of KL, and that's it. So it's easier if I do this by taking the v squared over 2g out of here, and just, even though I did this calculation already. So we know what this is. This is equal to what? 0.2 plus 0.2 plus 0.2. This is equal to 1. And this is going to be equal to 0.1. No, sorry. 0.02. 0.01. Remember, from Moody chart. This is going to be 10 meters, and this is 0.1 meters. So this is going to be 1 plus 10 to the minus 1 times 10 to the 1 is 10 to the minus 2 times 10 to the 1 is 10 to the minus 1. 10 to the minus 1 over 10 to the minus 1 is 1. Is that right? I think that is right. And then this is going to be 0.2 plus 0.2 plus 0.2, which is 1, which is then multiplied by v squared over 2g. And this velocity here is equal to 0.1 squared meters per second. This is 2 times 10. And if that's the expression I have, yeah, I won't do it. V squared over 2g, I don't know what's wrong with my pen, is equal to 5 meters. Getting kind of long, isn't it? So this is 5 meters. So we end up with a value of the pump head, which is equal to 1 plus 3 times 5 meters. This is in meters. This is dimensionless. This is in meters, which is 15 meters. Pump head is 15 meters. 16 meters. I can't count. And so now the coup de grace, I guess, is that we can calculate the pump head from the system. So pump head, which we have, is equal to the power multiplied by the, it's easiest to write it, I guess, as the unit weight times the volumetric flow rate. And so that gets rearranged to be the power being equal to the pump head, which we have in length, the unit weight of the fluid times the volumetric flow rate. This is equal to 16 meters. We know that the unit weight of water is equal to 1,000 kilograms times 10 meters per second squared, so it's 10 to the 4 newtons per meter cubed. And volumetric flow rate is equal to 10 meters a second multiplied by 10 to the minus 2 meters squared, right? Our diameter is 10 to the minus 1. Diameter squared gives us X. And this gives us 16 times 10 to the 3 Newton meters per second. So 16 kilowatts. So, which I looked up last night, which is, I don't know, 21 horsepower. I did it on Google, so I guess it may be or may not be right. So kind of a long process, but it is this chain. It's just a simple chain. We calculate the force we want to hold up, and that's going to be dictated by the velocity it squirts out of. So if we know that velocity, we can calculate the Reynolds number. The Reynolds number tells us everything we need to know about the conditions in the pipe, so we can calculate pump head. If we know the pump head, we can calculate its power. And so I don't really know, I'm not really a petrol head or a gas head, but a big powerful car is something like 300 horsepower, something like this. So this is a small car, I don't know, equivalent. You'd think that's what it is. I always used to think elite athletes were something like 500 watts or a kilowatt until I looked at my Strava the other day, and running the Pine Creek Canyon, I'd actually maxed out at 427 watts. So I guess peak athletes do better than that. So a peak athlete is something like 2.5 kilowatts running, I suppose, for short periods. And so this is in the ballpark. So that's the calculation sequence. So that's the kinds of things you might want to do in your stuff. That's not a hint, by the way. So.